Good day, everyone. We are here to present our research entitled High Performance of Conductive Polymers for Applications in Flexible and Wearable Electronics. Polymers are like big molecules with repeating parts, and they are super useful in today's technology. They are used in things like cool composites for airplanes and regular plastics for packaging. Now, some special polymers called conducting polymers are a big deal in making wearable technology materials. Think of wearable tech as gadgets you can wear like smartwatches or fitness trackers. These conducting polymers are great because they are flexible, stretchy, and work well with our skin. Imagine if your smartwatch could bend and stretch when you move, making it comfy to wear. Conducting polymers help with that. They also make sure the electronic parts in wearables work properly and efficiently.
Scientists study these polymers to make sure they are not just stretchy but also good at conducting electricity. That's important for things like sensors and circuit in wearable devices. Another big word is biocompatibility. It means that these polymers get along with our bodies, which is crucial if we want to wear tech directly on our skin without any issues. Also, these polymers need to stay reliable over time. You wouldn't want your cool wearable tech to stop working after a short while. So, researchers are figuring out how to make these polymers stable and long lasting. In the end, are working hard to understand how these special polymers behave so they can make better and more reliable materials for the cool gadgets we wear every day.
This study delves into discerning and comprehending the connections between the intrinsic characteristic of conductive polymers and their functionality in electronic devices. The research focuses on factors such as conductivity and various doping techniques, assessing their impact on electrical conductivity. Additionally, the study investigates the traits of flexibility and stretchability in these polymers, crucial aspects for their potential application in wearable electronics. The aim is to evaluate the overall appropriateness of these materials in this rapidly evolving field. Ultimately, the study aims to establish a knowledge foundation that will guide the design and advancement of more effective and dependable materials within the realm of flexible and wearable electronics.
The landscape of modern technology relies heavily on polymers, with applications ranging from aerospace engineering to everyday plastics. However, the focus has shifted to their innovative application in wearable electronics, notably with conductive polymers like polypyrrole and polythiophene. Mokhtar 2020 stressed the importance of these polymers in wearable technology due to their adaptability and biocompatibility, seamlessly integrating electrical components. Their versatility extends to battery electrodes, sensors, and protective coatings. Recent advancements in 3-substituted thiophenes and aniline derivatives have enhanced the processability of these polymers for wearables. Additionally, composite materials address biological challenges, paving the way for tissue-compatible soft electroactive materials.
The Seebeck coefficient and electrical conductivity of conjugate polymers are substantially influenced by the electronic band structure, namely the charge carrier density and mobility, in addition to the macromolecular design of conductive polymers, which allows virtually
The rapid development of portable or wearable electronic proposes new demands for energy storage devices. According to Chemical Society reviews, supercapacitors show great potential in portable or wearable applications. In these supercapacitors, conductive polymers are widely applied due to their high flexibility, conductivity, pseudo-capacitance, smart characteristics, and moderate preparation conditions.
In delving into the high-performance attributes of conductive polymers for flexible and wearable electronics, our methodology adopts a correlational research design. This approach serves to discern prevalence and relationships among key variables including conductivity, flexibility, and durability. In our study, we're exploring the superior qualities of conductive polymers that make them ideal for flexible and wearable electronics. Our research method is based on a correlational design, which means we're looking at how different factors to relate to each other, rather than trying to establish cause and effect. The key variables we're focusing on our conductivity, flexibility, and durability. We're trying to understand how prevalent these characteristics are in conductive polymers and how they interact with each other.
By emphasizing caution and proposing varied analytical approaches, our research seeks to facilitate a comprehensive understanding of the prevalence and effectiveness of these polymers in the dynamic realm of flexible and wearable electronics, ultimately contributing to the advancement of this field. This paragraph outlines our research methodology, which focuses on the caution and diverse analytical approaches. The goal is to enhance our understanding of polymer prevalence and effectiveness in flexible and wearable electronics. The aim is to contribute to the advancing this field by providing a comprehensive perspective.
Our research focuses on achieving optimal conductivity on conductive polymers for flexible and wearable electronics, a cornerstone in electronic device evolution. Conductive polymers with tunable properties, superior environmental stability, and ease of synthesis are extensively researched. Hybridization with other materials addresses inherent constraints, so we comprehensively examined polyacetylene, polypyrrole, polyaniline, polythiophene, and polystyrene sulfonate. Each presents unique properties contributing to electrical conductivity. For example, polyacetylene facilitates efficient charge transport. Polypyrrole offers tunable conductivity through redox processes. Polyaniline suits various electronic applications. Polythiophene provides high electrical conductivity with favorable processability. And polystyrene sulfonate combines conductivity with stability. Our findings contribute to the understanding of these polymers, opening avenues for application in diverse technological domains.
Research by Ouyang 2018 highlights polyethyllene's or PA's exceptional conductivity owing to its linear chain structure, with a conductivity similar to metals like copper and gold, up to 105 microsiemens per centimeters. PA's potential is remarkable, however, it's susceptible to rapid degradation in air due to oxidation, hinders its practical use. Similarly, polyaniline or PANI offers promise with its solubility in a conducting state, achieved by doping with large organic anions like dodecylbenzene sulfonic acid or DBSA or camphor sulfonic acid or CSA. This enhances its processability, especially in solvent like chloroform and M-cresol. Pani's side chain anions plays a pivotal role in reducing interchain interactions, aiding in its application in both organic solvent and water. Additionally, poly-3,4-ethylene dioxide thiophene polystyrene sulfonate or P.PSS emerges as a highly successful conductive polymer. Its solution processability thanks to PSS anions stabilizing the hydrophobic P-dot chains sets it apart. This polymer showcases exceptional traits such as high mechanical flexibility, biocompatibility, and transparency in a visible range as based on the study of He et al. In 2019. Ouyang's further study in 2021 reinforces P.PSS dominance in practical application due to its high conductivity, thermal stability, and solution processability. Unlike many intrinsically conductive polymers or ICPs, P.PSS water or polar organic solvent dispersibility, facilitated by PSS rule as a polymer surfactant, overcomes barriers in processability. In conclusion, while polyacetylene or PA and polyaniline or PANI exhibit impressive conductivity. Their challenges in stability and solubility, respectively, limits their practicality. On the other hand, poly-3,4-ethylene dioxide thiophene polystyrene sulfonate or P.PSS stand out as a highly successful and versatile conductive polymer, offering high conductivity, solution processability, and immense potential in flexible and wearable electronics.
So, in this section, we will discuss the results of doping techniques of various intrinsically conducting polymers or ICPs, including polyacetylene, polypyrrole, polyaniline, polythiophene, and poly-3,4-ethylene dioxide thiophene, polystyrene sulfonate, or P.PSS. First is polyacetylene is a well-researched ICP with unique conductivity properties that can be enhanced through chemical and electrochemical doping. So in chemical doping, it involves immersing PA in a dopant solution, such as iodine, creating positively charged solutions, thereby improving electrical conductivity. Otherwise, in electrochemical doping, it utilized an electrical potential to induce oxidation or reduction in generating charge polarons that contribute to increased conductivity. While the polypyrrole or PPY is extensively studied and can be doped using chemical or electrochemical methods. In chemical doping, it involves immersing PPY in a dopant solution, enhancing its conductivity, while in electrochemical doping, it applies an electrical potential to a PPY electrode, inducing oxidation and increasing the conductivity. However, the polyaniline or PAN-E is an ICP dope with acids bases or salts. In chemical doping commonly with sulfuric acid that can increases PANI's conductivity. In this research, it emphasized the intricate chemical processes and the importance of doping in optimizing PANI's properties for various applications.
Conjugated polymers are special materials widely used in making thin, flexible electronics and sensors due to their easy handling and ability to conduct electricity. These sensors particularly designed to detect dangerous chemicals like those used in warfare face a challenge in controlling their electrical conductivity effectively. One method, electrochemical oxidation, has limitation for mass production. Scientists discover an alternative called chemical doping, similar to adding special ingredients to enhance conductivity more particularly when making numerous sensors. Researchers aim to optimize these materials for effective use in electronics and sensors, especially in detecting harmful substances like chemical warfare agents. There's this special material called P.PSS, and it's like a successful superhero among conducting polymers. People use it a lot because it can be mixed with water and some special liquids, and we can easily make high quality films with it. The cool part is this materials is see-through. In the light we can see and it doesn't get messed up when it gets hot. But there's a little issue. It's not super good at conducting electricity. Now, scientists want to make it even better, especially for things like lights in plastic and solar cells. They found that using a specific liquid called DMSO helps a lot. It's like putting on sunglasses to reduce the sun's brightness. This liquid makes P.PSS work better by reducing the interference between the different charge in the material. Also, they found that depending on the type of P.PSS they use and the extra stuff they add, like ethylene glycol, it can become even better at conducting electricity. So, in simple terms, scientists are improving this superhero material to make it awesome for making see-through electronic stuff like light and solar cells. They are like chefs adding special ingredients to make the recipe.
Polyaniline is an intrinsically conductive polymer that can be doped with a variety of acids, bases, and salts to increase its conductivity. Doping mechanisms for PANI include charge, compensation, protonation, and radical formation. Chemical doping is the most common method for doping PANI. This method involves immersing PANI in a solution of dopant such as sulfuric acid, hydrochloric acid, or sulfuric acid. The dopant molecules insert themselves into the PANI chains, which increases the conductivity of the polymer.
Their work emphasizes the importance of doping strategies in enhancing the electrochemical performance of polyaniline. By summarizing recent developments, this review provides valuable insights into the ways in which doping techniques can be employed to optimize the functionality of conductive polymers for energy storage applications. This research highlights the crucial role of doping strategies in improving the electrochemical performance of polyaniline. Through a concise overview of recent developments, the review imparts valuable insights into the strategic applications of doping techniques for optimizing the functionality of conductive polymers. Specifically centered on energy storage applications, the study illuminates pathways to enhance the efficacy of these polymers, offering a comprehensive understanding of how doping can be leveraged for advanced energy storage systems.
Stretchability to polyethylene. One of the most significant conjugate polymers, P3HT, has been shown to have limited stretchability and low mobility. In this work, two polyethylene are prepared by attaching ester substituted biaxially extended conjugate side chains with backbones.
In the study of investigation of the mobility-stretchability relationship of ester substituted polyethylene derivatives macromolecules, the researchers find that the arrangement tendencies and stacking structures of polyethylene can be precisely adjusted through modification in side chains and backbones. The introduction of ester substitute side chains is identified as an effective means to enhance the charge mobility of the resulting polymers with additional improvement achieved through backbone planarization.
In this concluding section, we aim to distill the essence of our findings, drawing connections between the various threads of inquiry that have woven together to form a foundation of knowledge. Conclusion 1. The study highlights that conductive polymers, including polyacetylene, polyaniline, polythiophene, and polyethylene dioxythiophene, polystyrene sulfate, exhibit unique structural and chemical properties influencing their electrical conductivity. Despite challenges like low stability and restricted solubility, polyacetylene and polyaniline demonstrate high conductivity, while polyethylene dioxythiophene, polystyrene sulfonate, emerges as the most successful conductive polymer, offering high conductivity and biocompatibility, making it particularly significant for flexible and wearable electronics. Conclusion number 2. The study underscores significant advancement in enhancing the electrical and electrochemical properties of intrinsically conductive polymers or ICPs through doping approaches. Specifically, investigations into polyacetylene, a fundamental and extensively studied ICP, have revealed valuable insights through chemical doping, exemplified by iodine addition, elucidating the formation of positively charged solutions within the polymer backbone and subsequently improving electrical and conductivity. Additionally, electrochemical doping involving the application of electrical potential has been extensively explored to gain a deeper understanding of the generation and mobility of charged polarons within these polymers.
For the conclusion of flexibility, it results that polyaniline emerges as a highly promising and extensive research conducting polymer, distinguished by its remarkable stability, processability, and adjustable conducting and optical properties. The pH-dependent conductivity, along with distinct oxidation states, underscores the versatility of polyaniline for various applications. The unique combination of quinoid and benzoid rings in its polymer backbone results in the three oxidized states, each with distinct electrical properties. Notably, the flexibility of polyaniline, attributed to its reversible redox reactions, sets it apart from other conductive polymers like polypyrrole. While poly 3 and 4-ethylene dioxythiophene, or PEDOT, offers superior mechanical robustness, the selection between these polymers ultimately depends on the specific application requirements, balancing electrical conductivity with mechanical flexibility. The intricate interplay among dopant concentration, polymer structure, and oxidation states make polyaniline a compelling candidate for a broad spectrum of technological advancements. For the conclusion of stretchability, as a result, this study underscores the significance of tailoring side chains and backbones in polythiopenes to enhance their charge mobility and stretchability. The research concentrated on two key polythiopenes, the PDC-T2T and PDC-T2TF, incorporating ester substituted biaxially extended side chains with distinct backbones. It reveals a synergistic effect between backbone fluorination and ester substituted side chains, resulting in improved mobility stretchability properties, particularly in highly stretched states. The biaxially expanded side chains enhance intramolecular charge transfer and induce a more amorphous structure, while backbone fluorination steepens the structure, enhancing intrachain charge transfer. This expands the understanding of structure-property relationships in polythiopenes, providing valuable insights for the design and optimization of organic semiconductors. Additionally, it highlights the effectiveness of ester-substituted side chains in enhancing charge mobility as demonstrated by the highest observed hole mobility.
So, that concludes our study. Thank you for your attention and interest in our research. Stay curious and let's keep the spirit of inquiry alive. Goodbye for now.